Yeah, and make sure that people answer us questions. We cannot hear. So like when I hear, oh, if you could repeat, a lot of times people forget. If you forget, don't worry. But if you remember, good luck.
Thanks.
In general, we don't use it here, but if you want, we can provide one for you.
For the recording purpose.
No, we won't need it because the microphone is here already. Unless you don't feel you're not the first one here, and the people in general here, unless you feel your voice one. I don't think you will have a problem here. And this is a very good microphone. It's actually recording.
So if I'm turning.
Don't worry about it. We're fine.
All right.
Thank you, Armin. Appreciate it.
The beams are reflecting.
It wasn't like this. The building is starting to deform. This is a sensor we have here. Okay, the right size.
Student population. I don't know, there's a survey. That's a little bit close. The next thing is it was, huh?
It was advertised on our site.
For me?
It is on our front page.
Yeah, it is everywhere. It is on
Hi, Dr. Osita. Nice to meet you. I think I'm sending you the sealed applications in the past. Oh, from Berkeley. Yeah. Nice to meet you in person. Yeah, exactly. Do you have a daughter at Bentley? Yeah, okay. Yeah, that's the other connections.
Well, I know that Paul made an adjustment to this.
Which one? Oh, okay. Very nice. Yeah, time passes.
I think we should start.
Yeah. I'm looking forward to the talk. Thank you.
I think we should get started because there will be a class here starting at 1 o'clock, which should be done. And in fact, I would suggest, since there's so much space, come forward, come so we can see the slides better. For some reason, our projector has experienced a permanent displacement. And we have to make some adjustment. My name is Armin Derkuegen, and I'm a faculty member in charge of seminars this semester. This is the penultimate seminar we have this semester. The last one will be on November 22nd, 2 weeks from today. Today we have a very distinguished speaker, Simin naaseh, who is the president and chief CEO of Forel Assessor.
Forel Assessor, yes.
Yes, engineers in San Francisco. She's been working in structural engineering for 29 years. I think she started as a teenager.
Yes.
She has served as the president of the Structural Engineering Association of Northern California and is a member of several boards. Currently, she serves as a member of the OSHPD Hospital Building Safety Board. She's an allied member of the American Institute of Architecture San Francisco chapter. Rashid has been active on both the AIA Health Facilities Committee and the Innovative Seismic Design. I'm sorry, I missed the line. And the AIA Integrated Project Delivery Committee. She's well recognized for her experience in the implementation of innovative seismic design technologies such as base isolation. Several years ago, in fact, she gave a talk in this seminar series on the base isolation retrofit of the city hall, which was a fascinating topic. So, semm, naaseh.
Thank you,
I should
Armin.
add that it goes without saying that she's a fantastic role model for many of our students.
Thank you, Armin, and thank you everyone for being here. Thanks for inviting me. And
One more thing.
all right.
Please in the back, write your names. Those of you who have were having lunch, please write your name.
All right. Thank you for inviting me and for your kind introduction, Armin. When Armin asked me to come and present to you, I was thinking that perhaps I would show you some of the amazing projects that we've been doing on your campus. Citrus next door, the mother of all retrofit of the stadium, go Bears. But then I thought, I changed my mind. I decided to show you a project on one of the other UC campuses, UCSF. Not only because it's a very interesting and very challenging project, but also because it follows a project delivery method that is somewhat new to our industry, to the AEC industry, architectural engineering construction industry, and one that is changing the way we, the practicing engineers, are doing what we're doing. But I think it will also change the direction of the industry and how you as students and later professionals will be engaged in the industry. And I also think it's good for the school to be aware of the trend, so that when you're thinking about the curriculum and how best to align the curriculum with what the industry needs, I think this is an important phenomenon that is happening in the industry that would be of interest to all of you. So with that, I decided to present this project, which was a design-build project, but it also used a lot of the principles of what's known as the Integrated Project Delivery Process, otherwise known as IPD. So I will show you a little bit about what IPD is and what it requires from us design team members, and then I will show you the project and how we use the IPD to the advantage of delivering a successful project. Neither one works. All right. So before we talk about IPD, I'm going to just pause for a moment and talk about the traditional way that we deliver our projects. The projects are delivered in a design, bid, build atmosphere, meaning that we, the structural engineers, architects, we design the building, then we throw the drawings over the fence to our contractors who have a few weeks, couple of weeks to bid the drawings on the basis of, and be selected based on the lowest price most of the time, although not all the time, and then they build the project. By nature, this is a very silo-based process. It is very inefficient because we have these dividing lines between the design and the construction teams who are all working towards delivering a project. It's also inefficient because of that dividing line, we do a lot of non-productive work. What do I mean by that? Sometimes we draw a lot more than what a contractor needs to actually build the project. We draw a lot more for the attorneys. Why? Because the process tends to be litigious, and we just need to draw a lot more than is needed sometimes just to cover all bases. And you know, the litigious environment is probably what's governing all of this. The process doesn't encourage innovation, and it has, at the end of the day, very limited value added to the owners who are commissioning us to deliver the project for them. In contrast, IPD is a very integrated process, and it's a team-based approach to project delivery. It requires early involvement of all the key team members, both design team members as well as contractors and subcontractors. And this results in early resolution of issues, both design issues and construction issues. And it also encourages more communication sooner in the process of design and construction. In essence, what we're trying to get at is this. In this graph, if you look at the design effort and the impact of the design effort, and follow the project progress from the project development to schematic design, design development, construction documents, etc. The biggest influence that we can have as design team members or design and construction team members is at the beginning of the project. It's in this zone where we're at the early stage of the project development. And the impact of our influence drops dramatically as we go towards the end of the design and certainly into construction. At the same time, the cost of the changes, if they incur during this process, they are the lowest at the early stage of the project and highest at the later stage of the project. Now, the traditional project delivery method, if you can think of this dashed line as representing the process, the majority of the design activity does happen in this zone where we're in construction document phase. We're doing detailed design. We kind of ease into it from schematic design, design development phase, but do a lot of work in this phase. But if you try to find the intersection of these with the two other lines that I showed earlier about impact of our design and the cost impact, you can see that that level of effort really is inconsistent with the impact that it could have in the ultimate delivery of the project. So the blue line indicates how what we strive for in IPD, meaning that a lot more design effort, a lot of design thinking, a lot of collaborative thinking goes into the project early in the design phase, which means that ultimately, as we get closer to the end of the project, there's very little need for influence in design, and there's very little need for cost increase. So this is kind of what IPD strives for. So naturally, a collaborative process. The goals are aligned because the team members are all, they all have a seat at the table. They all collectively develop ideas and validate them and monitor their progress. And collectively, the team has the control of the project. It's not in the hands of the owner or the contractor or the architect, or it's in the collective control of all the team members. And as a result, there is a shared risk and reward potential depending on the outcome of the project. And this by itself becomes a huge motivator for everyone, not only to deliver what the project is asking for, but even for more. Because at the end of the day, we all have a skin at the game, and we are all going to get something if the project goes well. IPD requires a broad understanding of design and construction issues by all design and construction team members. And this is where I think it's important for you to understand that as civil engineers, structural engineers, that you're going to need to know more than just designing a building. You're going to need to know something about construction. You're going to need to know something about construction management. You're going to need to know something about architecture in order to be able to collaboratively work in this environment. And this is what is the change, the kind of a cultural shift that I'm talking about that will impact all of us down the road. The knowledge is not just about the work that they do, but it's about their challenges. What makes a contractor successful? What makes an architect successful? Or what obstacles do they have? If we all understand those things, we are able to better contribute to a collective decision-making process. Enhanced communication. And all of this may sound as motherhood and apple pie, but it's unfortunate that we don't practice these things currently in the traditional design project delivery. So there's just a lot more emphasis on communication and positive communication. There is need for easy and timely access to reliable models and sharing of those models. And this is where building information modeling and the various software such as Revit comes into play. It's become a huge part of what we do. In fact, that's all the tool that we use on all of our projects currently. So that knowledge of the tool is going to become important for your future. So now, with that background, I want to tell you about the project. As you can see, it's a very dramatic building. It's designed, the design is conceptualized by a very famous architect, Raphael Vignoli, from New York. And it's a design-build project, as I mentioned, with principles of IPD infused in it. The design-build process has several models. The one that we've used here is the bridging model. It means that there's an early bridging team who conceptualizes a design, and then another team comes forward, a design-build team comes forward and implements the design or completes the design, actually performs the design, and then takes it to construction. So our team, Farrell Alcesser, with DPR Construction and a Smith Group architects, were the team who came at the second half of the bridging process to design and deliver this project. And we had several members, and I've noted the key members who were actually there from day one as we were competing for the project, which we did. The building is nestled in the south side of the campus, for those of you who may be familiar with the Parnassus campus, in an area that no one would ever thought that you could build a building. It is just a very difficult and challenging site. It's serpentine shape, following the shape of the road, and it also follows the slope of the road. As the road slopes up, the building steps up in 450-foot long segments. It's a 600-foot long, 60-foot wide building. And it houses stem cell research laboratories, which is a very purposeful use, if you will, for the building. The project cost is $119 million, and the California Institute for Regeneration Medicine gave $35 million to the university in support of this building. With that funding came a string, and that was a delivery, a beneficial occupancy of the building by a certain date, meaning that if the university didn't occupy the building by that date, they would not get the $35 million. So it became the actual driver for the project and what we had to do in delivering the project. As I mentioned, the building, the design is a very brilliant design in that it actually uses this very difficult site to deliver a project that is so important for the heart of that research campus and to the hospital. But unfortunately, it was $20 million over budget when it was first conceived. And the university and the bridging team worked very hard on bringing the project to fit the budget, but they couldn't. And this is when the university decided to come up with a design-build approach and a competition to deliver the project. So our firm, along with our partners that I mentioned, we participated in this design-build competition process. And we came up with several innovative ideas that allowed us to cut $20 million off the project and also reduce the overall project schedule by 2 years, which is an incredible accomplishment. The project design was a very intense effort, and I'm not expecting you to read these dates or make sense of them, but just look at the shape of the schedule. Compared to any schedule that would be kind of a linear process with tasks back to back and a much more elongated shape, this one was stacked. It meant that we had to juggle several balls in the air. We were designing, our design was being reviewed, the contractor was fabricating what we were designing while we were designing the rest of the building. It was just one of those projects that required amazing management of what we were doing and also integrating it with the other design team members that I really believe would not have been possible had it not been for the way this project was being delivered. If it was a design-build project and somebody gave us this amount of time to design the building in vacuum, in our own silo, we couldn't have been able to deliver that. The IPD characteristics of the project, naturally a very collaborative work environment, because we as a team competed for the project, we as a team won the project, and we as a team worked on the project to its ultimate success. All of the consultants and subcontractors were on board early, the ones who could really make a big contribution, they were all on board. The original bridging team was engaged throughout the process. They were there in a review capacity, obviously to be sure that the design idea, the architectural design idea, was being implemented. Why? Because that's what the university bought, that's what a lot of the donors wanted, and if we were to change that, it would disrupt, obviously, the delivery of the project. The IPD advantages became that we had the constructability input from the contractor early in the project. Together we discussed the cost and benefit issues of various options that we were studying for the structural design of the project, and naturally a quick resolution of unforeseen issues, and there were many unforeseen issues because of the very aggressive project schedule that we had to follow, and because of the difficult site that we had. Well, looks like my plan views didn't make it in the transition from my computer to this computer, but elevations made it. You saw an earlier plan view of the building. As I said, it's a kind of a serpentine-shaped building. In elevation, basically the building is essentially a single-story building with some portions of it that has a second story overlooking some green roofs. And the superstructure is supported by a three-dimensional truss system, steel truss system, supported by isolators that are then supported on pedestals and drill piers. I'll have better views of this for you in detail later. There's a bridge that connects the building to the adjacent building and to the heart of the campus. Looks like my Revit model also didn't make it. Sorry. The performance criteria was that the building had to be fully operational in a design basis earthquake in a 475-year event, and operational in an MCE event. And the project was being peer reviewed by the bridging team. Now, when we design conventional buildings, we're always operating in the designing for life safety in, let's say, the 475-year event. That's what most of projects that are conventional code-compliant buildings are. When we have to deliver a better performing building, such as the one that we were talking about, for example, to be fully operational in a rare event, it becomes very difficult to use conventional structural systems and achieve that objective. And that's why this building is base isolated. That's one of the buildings why it's one of the reasons why it's base isolated. Typically, if you can think of the design basis earthquake and what the code requires for design, there's always a big gap between what we design for and what the real earthquake will deliver to the building. And the question is, how do we bridge that gap? And also, the gap is obviously much larger in this zone compared to this zone where the base isolated buildings will lie. For those of you who may not be familiar with the basics of base isolation, I'll just spend a couple minutes. Base isolation is a way to alter the dynamic response of the building by shifting the period of the building to be a longer period as opposed to a shorter period in this zone. And by doing so, the very first advantage is that we actually reduce the response of the dynamic response of the building by way of isolating it, and then damping and other factors obviously reduce it even further. And the other advantage of the base isolation is that it actually allows the building to move as a rigid body above the isolation plane, as opposed to having inner story drifts one floor relative to another and cause damage in the process. I'm happy to answer some questions later if you don't know enough about base isolation. The type of isolators that we used is the triple friction pendulum. This is showing the isolators in place, and this is showing a prototype isolator being tested. The design considerations were kind of global design considerations were site conditions, the complex geometry of this building, and the exposed structure, and I'll tell you what I mean by the exposed structure. Site conditions, it's a very steep hill, steeper than 45 degrees. The site is unstable, it has sliding issues, and there is an existing pump house which is over here, which is right underneath the building that we're trying to build, that feeds the hospital, the UCSF hospital. So we had to, at all times, we had to keep that operational as we were building our building around that. The geometry, you've seen some images of that. Obviously, the radial grid, the varying grades, the fact that the building stepped up, and the column tree design. We had to be very creative in coming up with a column tree configuration that was actually buildable and economically buildable. So these are some of the actual connections that we had to come up with. They're all sealed because this building is in a very corrosive environment, and we had to make all these connections sealed so that the structural members are not compromised later because of corrosion. We used the Revit model to model all of these, the entire building, and the contractor used a Tekla model. Tekla is another building information modeling software that tends to be more popular with contractors. So knowledge of both software in this day and age is a very useful thing. The exposure requirements. This is a typical day at UCSF. They tell us that the sun does shine occasionally, but every time I've been there, it's looked like this, hence the picture. And every time we brought a piece of steel, within a week, it was rusted or showed some beginnings of rust. So that's why we had to be extra careful with our connection details, etc. Other challenges, drill pier properties. Because the site is unstable and has varying subgrade conditions, the drill piers had to have different diameters. Because of the sloping road and the stepping building, also the projection of the drill pier above the grade varied. So some of them were above grade by about 20-some feet, some of them only a few feet. As a result, that they themselves had a displacement that varied that we had to worry about. So it wasn't like having a base isolated building on a flat ground where we don't have to worry about the displacement of the substructure. In this case, we also had a few inches of displacement that we had to worry about that was kind of varying along the length of the building. And the seismic overturning, obviously because of this configuration, the fact that it was a very narrow building and very little dead load on this uphill side of the building had a tendency to overturn, and we worked very hard to come up with a way to restrain that uplift. I mentioned the drill piers and the variable height. So this kind of illustrates the overturning issue and the narrow structure, and how this building will have a tendency to have an uplift because there is so little load. Majority of the load goes down to these isolators at the bottom of the hill, but the ones uphill see very little dead load to counteract the seismic overturning. And as you know, isolators have no tension capacity. This variety of isolators that we were using especially has no tension capacity. So we had to look for an external way to resist the uplift. In plan, we have isolators. The red dots, if you can see them, indicate the isolator locations, and the green dots indicate where we came up with external uplift devices that we use to counteract the uplift. 42 friction pendulum isolators and 8 uplift restraint devices that we had to use on the uplift side. Just to illustrate the uplift issue, in a typical isolated building, you would see some uplift, and you would see them perhaps at the corners of the building. If the building has kind of a more favorable geometry and configuration, you can perhaps get uplift in one instant, over the time history of the earthquake, and that wouldn't be detrimental to the performance of the building, and we would accept that in our design in those types of situations. In this case, because of the reasons I mentioned, the uplift was actually a much more serious issue, and not only did we have large uplift occurring on that side of the building, they were occurring in multiple cycles, but they would also have a tendency to stay up for some period, and in that period of time the building will actually be moving 26 inches, which was the maximum displacement. So we knew that we had to do something more effective or to resist the uplift. So by adding the uplift restraint design, we were able to limit the uplift to much smaller numbers and those that could be accommodated for by the device that we're using, and I'll explain what the device was. So the isolator manufacturers actually do make tension-capable isolators. This particular manufacturer does have a tension-capable isolator, but they're custom-made, they're unique to their process. So in order to build the 8 tension-capable isolators that we needed, they had to kind of stop their process of delivering the garden variety isolators, if you will, and change their processes to be able to deliver these 8. And it seemed like that wasn't going to be possible within the very tight schedule that we had for this project. So what we did was we invented our own. So we had some ideas, and some of you may know one of our principals at our office, Mason Walters, who came up with this brilliant idea of a new uplifter straight design that has never been used. And the evolution of this process was, it started out with a sketch, hand sketch, that Mason came up with. And then he actually overnight built a wood model at his garage. And this is a 3rd scale model. It's basically modeled after these roller skate rollers that he found in the neighborhood hardware store, and everything else was scaled around that. So in order to illustrate the concept of what this was, both internally and also we had to present it to our client, we made this wood model, which was extremely helpful way for us to communicate a very complex technical idea. We then started making, I think I may have lost a slide in the process. We then started making more detailed drawings. Then we built a prototype of this restraint device, which was tested at UC San Diego. And we validated the uplift restraint characteristics with this process. And we also had several models, electronic models along the way, that also was very helpful in terms of communicating the idea to various stakeholders. So basically the way this works is that there are 2 sets of rollers in perpendicular axis to each other, and they are connected by this connector system, and I'll turn this on again. Well, but by this connector assembly that is also articulated in 2 different directions. So these in this direction as well as this direction, and this basically allows the isolator to move not just the way this slide illustrates in orthogonal axis, but in all different directions. It's a combination of those 2 articulation, but also the fact that these pins that hold that have an axle holding the rollers together, they also have a full pin at the end, so they actually allow for the pins, for the rollers to also swivel, if you will, out of plane and accommodate for movement in all the various directions. We tested this at UC San Diego. This just shows, one direction of movement, but we actually did test it in all directions, basically following the same footprint that we had come up with from our, or similar footprint from what we had come up with in our design. And this is the uplift restraint in place. It's basically installed right next to a conventional isolator, and in its stationary position, basically. The rollers don't engage. There is a gap, and the 2 rails that are opposing each other, the radius of the rails match very closely the radius of the friction pendulum isolator, and naturally when the building moves and when it tries to engage, the rollers will basically follow the same pattern that the friction pendulum isolators will be following. Let's see. So I guess one of the lessons for us to learn was that this kind of invention, which we think is very cool, by the way, and we're very proud of it, would not have been possible if we were designing a building under this kind of an aggressive schedule, and if we weren't, and if we were dealing with it in the very constrained and litigious atmosphere that exists in the design bid build, because this is not something that we actually had come up with in the competition phase. In the competition phase, we had assumed that the schedule will allow the delivery of the tension capable isolators from the manufacturer. It was something that we learned later that may pose a risk to the project delivery in terms of schedule, and that's why we launched into this in the midst of all the other things that I mentioned we were doing, the juggling of all the other balls. The process was very conducive to this innovation, and otherwise we could not have been able to pull this off. So the reason why I chose to show this project is just some of these, and why we say that it spawns innovation is because the process actually allows for it. One of the things that, before we go to questions, I wanted to tell you, kind of relative to your engagement with an IPD world in your future, is something that our office has come up with. It's a new internship program that we've come up with, basically supporting the idea of an integrated project delivery. We're trying to fill a gap that may currently exist in our industry when students are still, for the most part, are studying in silo-based curriculum. And when they want to learn from internship programs, what we're allowing them to do is a rotating, essentially a rotate and intern program. This is something that our office came up with 2 summers ago. We've named it ISD, Integrated Skill Development, basically paralleling the IPD. And the goal is to expose the students to different aspects of the design and construction of projects. So this first time we tried it, we had 3 students. They were all engineering students. I think 2 of them were from your school. And they basically went around to architect's office, owner's office, contractor's office, and spent a portion of their internship time in those offices and learned about what their challenges are on a day-to-day basis. This past summer, we had architectural students and construction management students, as well as engineering students, who joined us in this internship program, and we rotated them again amongst the offices of the various team players. And I think it's an amazing way to kind of introduce younger students and future professionals to this whole cultural shift that's happening in our industry. And I'm hoping that some of you will be participants in that in the upcoming years. With that, any questions? I'm happy to answer.
Certainly a fascinating talk, a fascinating project. Can you have the light? Please, questions? Yes?
This is a very fascinating talk, as Professor Deputy mentioned. I was wondering if you want to talk about quality control issues, because this type of project delivery has been going on in macro Olympics with public-private partnerships.
Mm-hmm.
And I was wondering, in a typical project delivery, there will be an engineer side of quality control and a contractor side of quality control.
Mm-hmm.
How does that work in an integrated project delivery, and would the issues be covered up, or how would they be addressed, and
Mm-hmm.
how can the owner be out there?
So the question is, how are the quality control issues, both from the design side and the construction side, different in an IPD arena? Yes? Well, I have to say that the quality control process for us design team members comes from periodic site visits to the construction site, but primarily from an owner's inspection agencies who's there all the time and is actually inspecting, not just observing, the processes from concrete placement, concrete batching, welding, and all of the above. None of that changes, except that in this case, because it was design, build, and IPD, and we were all working as a team, we ended up spending a lot more time at the site than we would normally do in a conventional project. Normally, we would phase our visits to the site at various milestones. If they have a process that they're starting that will continue, that will repeat itself for many times, we would show up at the beginning of that process. In this case, it was just on an as-needed basis. Every day something came up and we had to be there and kind of work with the construction superintendent along with the architect to come up with the way to recover and recover fast.
Do you consider it to be a benefiting overall?
Oh, well, yes. And the benefit overall is the fact that the design quality control, because of the early involvement sooner idea that I mentioned earlier, we had very little conflicts. If you can imagine this building with this geometry, if we were to do it in our own silo-based models and never really shared and didn't have that interoperability of the models together, there would be many clashes with, various structural members with the architectural cladding or other things, or mechanical, electrical. But we were able to eliminate almost all of those. I think there were very few situations where we actually had to adjust things at the site. So one of the benefits of this of the IPD process is to have the tools to be able to share models early and to do the clash detections so that we don't have down the road to deal with the issues at the site. Does that answer your question? Yes.
So maybe this isn't something that you were kind of allowed to change by the design, but couldn't you have eliminated the uplift problem by bringing those piers outward to kind of balance the building?
By bringing the middle piers outward?
The ones with the tree trusses anchor. They look like they almost.
You mean these?
These,
you mean? No, the site is very constrained. I mean, the reason why the building is 60 foot wide and 600 foot long is that that's just the amount of land that is available to build this building. I mean, basically, this is, you see it here. And the design also, the other constraint was the architectural design. I mean, this geometry, although we changed it so that it was actually more easily constructible, that was one of the cost savings that we came up with, was very much a big part of the design, the architectural design, to the point that they're going to be putting LED lights on these members very soon. You'll all get to see them to actually, enhance the view of these. This is all going to remain exposed. It's one of the very nice things about this project, because our work actually does show, and then it's enhanced further by LED lights in the future.
Are the team members selected by the owner, or you as structural engineers, architects, and builders, you got together and jointly proposed or bid? What?
Right. So in a traditional project, most of the time, the owner selects the architect selects the structural engineer, and then separately there will be a process to select the contractor. Some variations of that, of course, but that's generally the case. In this case, we got together as a team. DPR was the contractor was the team leader, and they put together the team of Farrell, Assessor, Smith Group, and all the various other team members. And we competed with another similar team for this project. And one of the good things about this, which I think University of California, San Francisco, you should be very proud of, is that they actually funded the competition process. They funded it so that, and that allowed us to really dive deep into the technical issues in the 2-month competition process that we had, so that we eliminated the uncertainties as much as possible. And when they gave us the authorization to proceed, we could just hit the ground running and go for the 2-year, total of 2 years design and construction for the project. That's what the schedule was. So I think not only the process, but the fact that there was funding for that competition phase, which is not always the case, that also really benefited the university at the end of the day. It was a small expenditure compared to the value that they gained.
Yes, sir.
Was this project reviewed by Oshkosh?
No, this is not a hospital project, and there was a nervous moment over the design of the project because that pump house that I mentioned is right underneath our building, and I think there was some nervousness that because of that maybe we will have to go through Oshkosh. It turned out that was not necessary, but it does.
And it was designed based on ASC 705?
Yes.
Yes.
One of the strengths of BIM software is that you can work with a 3D model and defining dimensions. orthogonal walls. And I was just wondering, with curved structures like this, if you're trying to take a section out for the plan use or elevations, how would you be able to account for the curvature and the actual real lengths of, let's say, like the diagonal breaks?
Right. The question is, how did we use the BIM model in validating the geometry or coming up with the geometry or getting plans and sections out of the model? BIM is a very good tool, a very good three-dimensional tool for design. It's not yet a very good drafting tool. So, you know, the idea of BIM is we're trying to use BIM. It's at its infancy. We're trying to use that. At the same time, we're trying to collapse it into two-dimensional drawings and print multiple copies of it and distribute it, just the way we've been doing it for years and years. BIM is not meant to do that, but we're kind of in that transition mode. So to answer your question, it's not very easy to get plans and elevations in the same way that we're accustomed to seeing in other projects. You have to work very hard to make them legible and good looking, which is, you know, what we like to do on CAD drawings. But it's very powerful as a three-dimensional model, and when we merge the model, our model, the architect's model, the mechanical engineer's model, it's a very powerful tool to kind of coordinate the different elements that go into the building. It's the BIM models, the BIM software, Revit is the one that is most commonly used, is still evolving, and it's not very conducive to curved. Actually, one of our first experiences using Revit structures was the Memorial Stadium project, the Student Athletes High Performance Center, which has the curved configuration, and Revit just didn't do that. So it took us months to come up with, you know, a very an elegant or useful even BIM model. But along the way, the software evolved, and I think we helped the software to evolve.
Okay, take one more.
Were there any, given the nature of the research that's done there, were there any special design criteria? You mentioned that it was operational in a 75-year event. Were there any criteria, accelerations or drift?
There was not. What I showed here is what was in a basis of design document that the UCSF and their bridging team produced, and that was the extent of it. There were more specific criteria for vibration design, for example, to support the nature of the research that they do. And that even was not an unachievable criteria. Actually, the most difficult one that we've worked on was the Citrus building. You know, vibration 200 MIPS, I think, is what we designed the floors for. Those the imaging areas are designed for 2,000 MIPS, I believe, and the offices for 4,000 and 8,000 to that range. So in terms of seismic criteria, there wasn't anything more specific than that. I think the base isolation idea came both as a desire from the university to have a higher performance building, but it also really was the only way that enabled this architecture. I don't think we could have designed this building on that site with those constraints in an economical way without base isolation. So this was actually one of the cases where base isolation made the building economically feasible and enabled the very dramatic architecture.
Was there a collapse prevention check at a 2,500-year level?
I think we did that as a side. I think that was a side consideration that we had. There wasn't anything in the basis of design document.
So say a CE7 would suggest that you need to look at it.
I think that was a kind of a side consideration outside of the requirements of the project that we did.
Well, thank you very much.
You're welcome. Thank you.
That's some of our students. These are undergraduates or graduate students?
Well, most of the ones who have come to us are kind of, you know, starting their graduate programs. But there's no reason why it wouldn't apply to undergraduate students either.
Sorry,
all right, thank you. It's all right. No, I know.
Talking about
Would you like to
Spelling mistakes.
Sorry.
You asked me about spelling.